For this final part on bonding theories, I want to discuss reactive carbon intermediates. These are going to be things like carbons with lone pairs or incomplete octets that make them more reactive than just your typical carbons. I'll begin by talking about carbocations. The simplest example of one of these is the methyl cation, CH3+. The carbon of a carbocation has 3 groups around it, the carbon's 3 bonds. The carbon is therefore sp2 hybridized, and it has an incomplete octet. Because of its hybridization, the carbon is trigonal planar. In terms of reactivity, we have to think about carbon's empty p orbital. This is where a nucleophile would attack. In Chem 230 and 331, we talked about how alkyl substitution can increase how stable a carbocation is. A tertiary carbocation is the most stable. This is where your carbocation center is attached to 3 other carbons. This is followed by secondary carbocations, primary carbocations, and then the least stable carbocation is the methyl one, where you have just hydrogens rather than alkyl groups. I'm going to show the orbital overlap in the ethyl cation that stabilizes it a bit compared to the methyl carbocation. I'm drawing the carbocation center toward the right side of the molecule. I'm showing its empty p orbital, and for this carbon I'm showing a side-on view. So notice that my p orbital here lies in the plane of the page. Adjacent to my carbocation is my methyl substituent, and I've drawn out the 3 hydrogens of it here. In its current conformation, only one of these CH bonds can overlap with this empty p orbital. And that is the carbon-hydrogen bond that's in the page. The hydrogens that are wedged or dashed are not oriented correctly in space to overlap with the p orbital that's in the page. So my carbocation with its empty p orbital is a really great electrophile, and I'm going to think about how this neighboring carbon-hydrogen bond can donate electron density toward the carbocation. Here I've drawn the overlap of the carbon sp3 hybrid orbital with the hydrogen s orbital. As I've drawn it here, notice that I have a shading match on the top side of my molecule, as well as a little bit of overlap from shaded lobes on the bottom side of my molecule. If I want to describe this interaction in terms of frontier molecular orbital overlap, I would say that I have a sigma bond, that's a carbon-hydrogen bond, that's donating into the empty p orbital of my carbocation. So something electron-rich donating to something electron-poor. This type of interaction is called hyperconjugation. This is a donation of electron density from a carbon-hydrogen bond into an empty p orbital. But importantly, you have to have proper alignment of your carbon-hydrogen bond for this to occur. This bond needs to be in the same plane as your p orbital. A type of reaction that carbocations can undergo are rearrangement reactions. When we saw these in Chem 230, we only considered that carbocation rearrangements would occur if you make the carbocation more stable. For example, if you started out with a primary carbocation and had a rearrangement to form a tertiary one, that would be favorable because it would make the carbocation more stable. In reality, carbocations are extremely reactive, and carbocation rearrangements can occur even if they don't make a more stable carbocation. Returning again to the ethyl carbocation, Notice here that my carbocation is primary. To draw a carbocation rearrangement, I would draw my arrow from the middle of the CH bond to the carbocation center. This causes that hydrogen with the 2 electrons from the carbon-hydrogen bond to hop to the carbon that was formerly the carbocation, and the carbon, in this case on the left, that lost its CH bond is our new carbocation. In the case of the ethyl cation, this is also a primary carbocation. Based on Chem 230, you would predict that this reaction wouldn't occur because it leads to a molecule that is equally stable. In reality, this rearrangement, known as a hydride shift, is occurring extremely rapidly, even at low temperatures. If you imagine what the transition state for this rearrangement might look like, you could imagine that this hydrogen that's moving is halfway between the carbon on the left and the carbon on the right. I'm breaking the carbon-hydrogen bond from the left and forming the carbon-hydrogen bond on the right at the same time. I'm using the dotted lines here to represent my breaking and forming bonds. In the case of the ethyl cation, it's actually been very seriously debated whether or not this structure represents an intermediate or a transition state. I'll delve more into the definitions of transition states and intermediates later in the course, but this argument essentially comes down to, does this bridged structure last longer than the time scale of a bond vibration? And it turns out that it's still being debated among organic chemists whether or not this is an intermediate or transition state, or essentially how long it exists in this type of bridge structure. I next want to talk about carbanions. The simplest example of this would be the methyl anion. In contrast to carbocations, these have 4 electron groups around carbon. You have your 3 bonds, but now you have a lone pair. And because you have 4 groups around carbon, these are sp3 hybridized. The carbon would be trigonal pyramidal, and the lone pair occupies an sp3 hybrid orbital. One thing worth considering is, could carbanions be chiral? Imagine a scenario where you had a carbanion carbon with 3 different groups around the carbon, labeled R1, R2, and R3, and then you have a 4th group, which is your lone pair. This carbon, because it has 4 different groups around it, could be considered chiral. And so you could imagine that you could have a chiral sample of this molecule, this single enantiomer, if not for one problem, which is that carbanions can invert. This inversion involves a differing position of the lone pair in the molecule. For example, going from the top part of the molecule down to the bottom, where the R groups are shifting up on the page, but otherwise not changing positions with each other. The relationship between the carbanion on the left and on the right is that they are enantiomers, or rather, they are non-superimposable mirror images of each other. If we want to imagine what the transition state to this inversion looks like, you would have your lone pair at the transition state in a p orbital, which is unhybridized, making your transition state trigonal planar in geometry. Although how fast this inversion process takes place depends on temperature. Usually you can't bottle 1 enantiomer of a carbanion because it'll usually racemize by this inversion pathway rapidly, at least close to room temperature. In terms of hybridization in geometry, radicals are a bit more complicated than carbocations or carbanions. As a reminder, our radicals contain an unpaired electron on carbon, These are neutral compounds with 7 valence electrons, and their hybridization and geometry depend a lot on the substituents on carbon. We'll compare 2 examples, a CH3 radical, methyl radical, or a CF3 radical, a trifluoromethyl radical. In the case of the methyl radical, this is thought to be planar and sp2 hybridized. This would mean that the radical, or unpaired electron, is occupying a p orbital on carbon, rather than a hybrid orbital. But it's been observed that it's not very much higher in energy to be pyramidal, so you can think about the methyl radical as also having access to a trigonal pyramidal geometry as well. In contrast, the CF3 radical is trigonal pyramidal, and the carbon is sp3 hybridized. This means that the unpaired electron occupies an sp3 hybrid orbital. Fluorines are pretty close in size to hydrogens, so our explanation of this difference in geometry has to rely on electronic factors rather than steric ones. And it really comes down to what type of orbitals carbon is using to make its bonds to fluorine rather than where the electron goes. So fluorine is our most electronegative element, and it draws electron density really well to itself. Because of this, fluorine prefers to bond to carbon if carbon is using an orbital where it can withdraw more electron density. If the carbon is sp3 hybridized, the carbon-fluorine bond is made up from carbon's sp3 orbital. Because sp3 orbitals are made up from mixing one s orbital with 3 p orbitals, you can think about this orbital as being 25% s in character. Instead, an sp2 orbital would be made up from an s orbital and 2 p orbitals, making the orbitals have 33% s character instead. S orbitals are closer to a nucleus than p orbitals. So in terms of ease of withdrawing electron density, the more p character an orbital has, or the less s character it has, the easier it is to withdraw electron density. This means that fluorine is able to withdraw more electron density from carbon if carbon uses an sp3 orbital to bond to fluorine, and this stabilizes carbon being in the sp3 hybridization. The last type of reactive carbon intermediate that I want to talk about are what are known as carbenes. You haven't seen these previously, unlike the other examples. Carbenes are neutral molecules where you have a carbon with a lone pair and 2 substituents. Here the R could be a carbon, a hydrogen, really anything. Notice that the carbon just has 2 bonds and a lone pair, so it only has 6 electrons around it, making it have an incomplete octet. However, this carbon is uncharged. The simplest example of a carbene is CH2 with a lone pair. Depending on where we put the electrons from the lone pair, you can get 2 different possibilities for how the electrons will be arranged in your carbene. In one possibility, the carbon is going to be bent, but it's going to be what's known as a triplet carbene. The term triplet refers to the carbon having 2 unpaired electrons. In this case, one unpaired electron goes in an sp2 hybrid orbital. This goes in the same plane as the 2 hydrogens. And the other unpaired electron goes in a p orbital. In the triplet carbene, these two electrons will have their spins oriented in the same direction rather than canceling each other out. Our other option is that the carbon and its bonds to hydrogen are still bent, but we put both of the electrons in the hybrid orbital. This gives us what's known as a singlet carbene. We still have sp2 hybridization, but now both electrons go in the sp2 hybrid orbital that's in the same plane as the hydrogens, and carbon has an empty p orbital. But in summary, I've talked about 4 different types of reactive carbon compounds. These could be carbocations, carbanions, radicals, or a new type called carbenes. So far, I've mostly focused on hybridization and geometry of these, but later in the semester we'll get to reactivity. That's it for this video, and I'll see you in class.